Yes.
Yeah, it's my pleasure to introduce Brian. So he comes here from MIT, but before that he was across the bay at Berkeley, and for his PhD he did quantum optics with what I'm told are real photons, not microwave photons, and he, so he did quantum optics and then materials and things like that for his PhD. But then, for his postdoc, he kind of got introduced to the dark side, doing superconducting circuits with your friend Speaky. And this was really fortuitous for our whole community because he brought that kind of optics knowledge with him, and he, among other things, developed the common wave parametric amplifier that a lot of us use now. And so he did that, and he has a footback. Then now he's gone to MIT where he's faculty, and he's taken that significantly further, and I think as well as developing new types of couplers that can really dramatically enhance the coupling between qubits and resonators and each other. And I think again, I think it's really nice to have him here because I think one thing that's special about like applied physics and EE here is this kind of there is this really nice back and forth between kind of the kind of optical photonics and quantum engineering and circuits. And so I think Kevin really exemplifies this kind of thinking, and so I think it's going to be a real.
Yeah, thank you so much, Dave. It's an absolute pleasure to be here. I really feel that microwaves are photons too. But I came from physics and optics, and now I'm in electrical engineering and microwaves. So it's been like a kid in a candy shop, learning all the like classical microwave engineering techniques and computer science techniques. And I'll tell you about some of these in the talk today. So I'm going to talk primarily about broadband quantum limited amplifiers and their design, fabrication, and some of the exciting new results we have. I put the couplers in the backup slides. So if you have questions about those, absolutely ask. But given all the people, the detector folks here, I wanted to, and fab folks, I wanted to focus on these things. So Will Oliver has this very nice analogy that superconducting or quantum computing in general was sort of at the stage of the original Wright flyer, where we had the initial flight, we had the initial proof of concept, but you're not going to be riding a Wright flyer across the ocean or using it for something useful. And quantum computing is sort of at that stage where it works, but you're not able to simulate useful problems yet. And the question is, how do we get from that Wright flyer to something that I can fly from Boston to SFO? And a lot of that is unknown. It's fundamental science and engineering problems, as well as a lot of investment and a lot of hard work. And in my group, we're really interested in solving some of these foundational hardware challenges in quantum engineering. For example, what are the fundamental limits on device performance posed by quantum mechanics? How can we engineer devices, apply all these cool engineering techniques to reach these limits? And can those limits be surpassed with clever physics or engineering? In this talk, I'm going to give a brief introduction to why quantum limited amplifiers are important, and why did broadband amplifiers, until very recently, I would say the last 2-3 weeks, have lower quantum efficiency than narrowband amplifiers. And some stuff we've been doing on applying electrical engineering simulation and modeling techniques to develop open source tools so you can simulate these things very quickly and easily. And then I'm going to talk about our demonstration of a high quantum efficiency Floquet mode, Josephson traveling wave parametric amplifier, and some paths to broadband amplification with passive isolation. Okay, so why are quantum limited amplifiers important? As Dave was telling you, it's really important for qubit readout, because having a better preamplifier allows you to measure faster. So, there's a trade-off between SNR squared is proportional to the quantum efficiency of your amplifier from 0 to 1. The decay rate of your amplifier, or the decay rate of your resonator, the number of photons in your cavity, and time. So if you can 10x the quantum efficiency of your amplifier, then you can read out in 1/10 the time. And typically, by going from having no quantum limited parametric amplifiers, and having a quantum limited parametric amplifier, you can indeed improve your efficiency by about an order. These quantum limited amplifiers, they may hurt or help qubit coherence. They can hurt it by dephasing your qubit, for example, from the strong pumps of your amplifiers, or they can help if they have built-in isolation. And they also enable multiplexing to reduce resource requirements for scale. For example, when you're building a quantum computer with even 10 qubits, if you can have only one readout chain, then that really makes things a lot easier. So why do we need parametric amplifiers at all? It's actually interesting if you read the history of parametric amplifiers. When vacuum tubes were first developed, and even before then, people were excited about parametric amplifiers at microwave frequencies. But then transistor amplifiers and transistor devices in general got good enough and just entirely crushed that field. But parametric amplifiers remained important in optics. And now in superconducting devices, parametric amplifiers are again important at microwave frequencies because they can achieve lower noise performance. So if you look at this plot from Austin Minnick from Caltech, plots the noise temperature as a function of frequency for a bunch of different amplifier technologies and amplifier papers. And you see that typically all of the semiconductor amplifiers, they're even noisier than this line drawn at 3 times the quantum limit. And they also generate a lot of heat. And it's hard to dissipate that heat at cryogenic, at millocarbon temperatures. So we want amplifiers that operate at this quantum limit and dissipate very, very little heat. Whether this will change in the future, I don't know. I think I'm not an expert on these semiconductor amplifiers, but I think if one could improve these, that would be very exciting as well. So there have been typically 2 ways of building parametric amplifiers made out of Josephson junctions. The first way that was explored is essentially making an LC resonator with a capacitor and a Josephson junction in parallel. And a Josephson junction acts like a nonlinear inductor. So when you drive this system, it becomes nonlinear and you can achieve parametric amplification. This one, as drawn, it has a fairly narrow bandwidth and it has a bandwidth quality factor trade-off. By performing various types of impedance engineering, you can increase the bandwidth of these amplifiers and you can get up to hundreds of megahertz of bandwidth at, say, 5 gigahertz. These are well understood and have near unity quantum efficiency. They're almost perfect amplifiers in that noise sense. For example, 80% has been measured from this work by Andrew Edits. The other approach is what I'm talking about today. These are Josephson traveling wave parametric amplifiers, where the idea is to, these are sort of the traveling wave parametric amplifiers or fiber optic parametric amplifiers if you're from the optics community, where you make a long line of Josephson junctions and capacitors to ground, an LC ladder, a nonlinear LC ladder transmission line, and your pump and signal propagate through this long line and are amplified as they go through this. These are much more complicated devices. They have thousands of spatial modes. They have a wide bandwidth because they're intrinsically broadband. Nothing is going to cut off the bandwidth, and they have potential for broadband isolation. But can they reach the quantum limit? That's been one question that's really bugged me since we did these initial works in these amplifiers. So many people in the community say, okay, these broadband amplifiers, they're nice, they provide high gain, they have a lot of bandwidth, but I really want high quantum efficiency, so I'm gonna go use a JPA. I think that this is an interesting technological problem and an interesting physics problem as well. Can they reach the quantum limit and how to design them in a way? So
that's a basic question. So are you thinking of using amplifiers in cases that are already used, but but making them better?
Yeah,
or is this designing amplifiers for quantum computing?
So I get that's a great question, and one of the reasons why I'm here talking with folks. So a lot of the work in my group is focused on building amplifier computers, and they're the the demands and the specs that you want are pretty well known and understood. And they're even small performance benefits, even a factor of 2, for example, it can really improve your ability to do error correction. So that's one of the motivations for this work. But I think another is that the quantum computing community has spent a lot of resources developing these really, useful and powerful technology. And what other fields could this be used for? So I'm really interested in answering that question. I would love input from all of you. And like, are there uses for these? Thank you. Any other questions before I move on? Thanks. Okay, so people have made a bunch of these traveling wave parametric amplifiers, but as I mentioned, they're not yet ideal amplifiers. For example, here was the work from 2015 from Irfan Siddiqui's group in collaboration with MIT Lincoln Laboratory. Where you can see broadband over 20 dB gain over several gigahertz. There's been a lot of nice work from Nico Roche's group at Grenoble. There's been nice work from NIST and CU Boulder on using, instead of Josephson junctions as the nonlinear medium, using kinetic inductors, where these are superconductors where as you put more current through them, their inductance will change. And these are nice for very high power handling amplifiers. And also nice work out of Caltech and JPL on using kinetic inductors with this amorphous silicon to act as a high Q capacity. But none of these amplifiers really reach the quantum limit, and they all have some like issues like ripples and things like that, and other non-idealities. So we'd like to understand this. So the Josephson traveling wave parametric amplifiers, these are, say, one of the standard amplifiers for superconducting qubit readout. They have bandwidth and dynamic range to simultaneously measure tens of qubits. The P1 dBs, depending on design, from -100 to -85 dBm. P1 dB is the power, the input power at which the gain drops by 1 dB. So it's basically the power handling. And this is a very small amount of power for like room temperature daily life things, but it's also larger than like what your GPS uses, for example. And these devices were fabricated at Lincoln Labs, and they've distributed 400 plus of these worldwide to quantum limited readout for the community, and they're produced by several companies nowadays. But they don't have this ideal quantum efficiency. And the question is why? So let's first look at what their quantum efficiency is and break down the quantum efficiency budget. So if we look at the experimental setup where we have a 3D frame bond, it's a qubit with an isolator and directional coupler to couple in the pump, and the amplifier followed by the rest of the readout chain. You can use the qubit as a power calibration and then get the input referred noise, measure the noise on the spectrum analyzer, and use the qubit to get the input referred noise power, so you can measure the effective input noise of the tuba at the position of the qubit. And what you see when you do that is a quantum efficiency relative to the ideal parametric amplifier, an ideal phase preserving parametric amplifier of about 50%. So you're a factor of 2 away from the best that one could do. So if we break down that budget, we see that about 30% of that is from the insertion loss between the isolator and the coupler. About 10% of that is due to the lossy dielectrics in the tuba. Basically, if you're familiar with the beam splitter model from caves for quantum noise, the loss in the tuba will absorb some of the power, and then it will emit vacuum fluctuations back into your system, and this will degrade this performance of your amplifier. Your following amplifier contributes 7%, and then there's this unaccounted for drop in quantum efficiency of 17%. And like, the physicist in me is like, what's causing that? What could possibly be causing it? It's something that doesn't show up in any of these models, but is degrading in your device. So figuring that out and solving it has been one of the focuses of my group at MIT. And what we realized is that this unaccounted for noise source is where, if you look in this diagram, you have the signal that you input into your device, and this is coupled through the pump to something called the idler. And this is something that's generated in the parametric process, and often people just don't do anything with this idler. But the critical thing is that this pump not only couples you to the idler that you need, but it also couples you to a bunch of other idlers that you don't necessarily want. But because it's a broadband device, all of these idlers can propagate. And this is really analogous to qubit leakage from the pump from subspace in qubits, where if you're familiar with a qubit, for example, superconducting qubits, you often work with the ground state of the system, maybe the first excited state, and then these transmon qubits will have a bunch of other levels. And typically you just ignore them. But if you drive the system too quickly, then you might excite your qubit state to these higher levels. And this can act as a source of decoherence. It can mess up your calculations. And that's very similar to what's happening here. In these amplifiers, you inject your signal, and you get an amplified signal, an amplified idler, and then you generate all these sidebands, which you don't measure. And that information is in this amplifier that I'm about to describe, you can coherently get rid of all of these sidebands, and you can recover that loss mechanism. So the way to think about this is, I think as both like physicists and engineers, probably you're familiar with eigenmodes of a system, right? If you initialize a system in its eigenmode, what's it going to do? It's going to stay in that eigenmode, and then it might, as a function of time, acquire some phase, but it's going to stay in that eigenmode. And eigenmodes are the actual basis for a time-independent system, a linear time-independent system. But if you have a system that is periodically time-varying, for example, these driven systems, they're periodically, you can view the dynamics for the weak signal and idler as linear, periodically time-varying systems. And the analogy to eigenmodes in that is something called Floquet modes. And these are sort of similar to eigenmodes, except they involve components at different frequencies. So it's like an eigenmode that has something at this frequency and also some amplitude at a bunch of different other frequencies. So these are really the right basis to think about these periodically time systems, and Floquet modes are used in a lot of things with qubit driving. But here we're applying this to amplifiers. So let's first look at the amplifier dynamics in this Floquet basis. So this is just looking at, for a traveling wave parametric amplifier, injecting the signal and seeing as you propagate inside the device, you generate an amplified signal. And you also generate an amplified idler. Then you generate all these other modes as well. These are those sidebands that are degrading your efficiency. And the dynamics just look really messy, right? Like it's what's going on there. But now if we take this exact same system and we just do the decomposition into these Floquet modes, then we see that it looks really simple now. All we see is one Floquet mode where you have this amplification, one Floquet mode where you have this deamplification, and all these other Floquet modes that just aren't doing anything at all. They're just sitting there and acquiring a real phase. Whereas these Floquet modes, they're acquiring a complex phase that is that's giving you amplification or deamplification. Okay, so this is nice, a good way of looking at your amplifier, but now we need to somehow put our signal into this Floquet mode that we want. And you really could do this by like sending in 10 different frequencies of your signal, getting the amplitudes and phases right to form that Floquet mode. But that would be an absolute nightmare. Like as an experimentalist, you want to send in one frequency to your amplifier. You don't want to like fine tune what you're putting in. So our idea was to adiabatically vary the nonlinearity of the system. So we start with very linear junctions on one side, and then decrease the size of the Josephson junctions towards the middle. And decreasing the size makes them more nonlinear. So this sort of adiabatically transforms you from the Floquet modes in free space, which are just eigenmodes because it's a linear system, into the Floquet modes in your driven nonlinear system, and then back again. And what that does is it completely eliminates that sideband source of noise. So this is, in a realistic device where we're not ramping the nonlinearity down to 0 at the ends. It's like I don't know, was this 10% or something like that, or no, a factor of 4 or 5. And we don't ramp it completely down to linear because of the dynamic range limitations of your JJ. Like linear would mean an infinitely big Josephson junction. So here's a conventional tuple where we keep the junctions the same. Here's a Floquet tuple where we vary the size of the junctions in order to change the pump current relative to the critical. And in the normal one, you see the dynamics that I was showing earlier. In the Floquet device, you see that you still generate the signal and the amplified signal in the idler. But now as you ramp down the nonlinearity, then you see that you sort of like slurp up all these sidebands and they go away at the end of the device. Okay, so, and you get actually the same amount of sidebands in the middle of the device. Anyway, you get the same amount of sidebands in the middle of the device, but then at the end of the device, they've gone away. And it's really instructive to think about this, what happens when you inject noise. So when you inject noise at one of these sideband frequencies, and you always have noise, you have vacuum noise being input into your system. So in the normal tupa, you inject noise, and then some of that noise results in, is mapped into the signal in idler frequencies. And that noise comes up in your output frequencies. Whereas in the Floquet tupa, that noise is just entirely, it goes into one of the Floquet modes of the device that are entirely decoupled from the gain of your device. So those Floquet modes just don't, it just remains decoupled from your signal in idler frequencies. So it doesn't increase the impact the noise performance of your device. And if we compute the quantum efficiency, we can take two devices, the blue and the red curve, that have very similar gain performances. But if we plot the quantum one minus the quantum efficiency relative to the ideal, we see that the Floquet device has a dramatic improvement in the expected performance. And to be completely honest, when we started this project, I was thinking that this is going to be a solid engineering work where we're going to vary the cutoff frequency of the device, and we're going to see a gain bandwidth trade-off. The more narrow band you make your amplifier, the higher the quantum efficiency will be, and depending on your application, you might pick some bandwidth. But what we found was this Floquet mechanism that there is no gain band, or there is no bandwidth quantum efficiency trade-off, which I think is pretty cool. Okay, so now I want to talk about how to simulate these things. So this, if you read the paper on this, it was pretty complicated analytic decompositions into this Floquet basis, and you can't simulate a lot of realistic performance parameters like what happens if your junctions vary a little bit from the ideal. And this is sort of I think a common thing in our field. We will treat things the physics way using coupled mode theory and analytic solutions and things like that, which is good. But if you talk to electrical engineers, they'll say, oh, just run a SPICE simulation. And running SPICE simulations is challenging for these types of systems. And we've actually done a lot of work in applying these electrical engineering techniques to compute the noise performance of these, and working with Keysight to allow you to simulate these sorts of noise mechanisms in their software as well. So I'm going to tell you about some of that. So along those, I want to tell you about this JosephsonCircuits.jl open source harmonic balance simulator that my group developed. It's a Julia package. You can just go download it from the general registry. It's quite fast. People often simulate these things using software called WR-SPICE, which performs time domain simulation. It's a SPICE simulator that can simulate things in the time domain, including Josephson junctions. But the time domain is not really the right way the efficient way to think about these systems, because it has a discrete set of spectral modes. To simulate this in the time domain, you have to simulate it until it reaches steady state, it takes a long time. If you simulate this using something called harmonic balance or multi-tone harmonic balance, where you only simulate the specific sets of frequencies that you need, then we find that this is about 10,000 times faster than simulating these things in WR-SPICE. And we published a cross-validation of this code along with ADS and used these X-parameter framework to describe the quantum efficiency of these devices. X-parameters, if you haven't heard of these are a multi-frequency generalization of scattering parameters. So scattering parameters relate the inputs and outputs in a multi-port system, the reflection, transmission, etc. But typically they're only at a single frequency. X-parameters generalize this to interactions between frequencies. And at least in superconducting circuits, we sort of used multi-frequency scattering parameters a lot already. We just call them scattering parameters. But I think it's good to know that the electrical engineering community has this thing called X parameters because they put a lot of care into like how to measure these, all the phase normalization conventions and things like that. So I would encourage you, if you're doing that, to look up some of these papers. So the software can compute gain and scattering parameters. It can be quantum efficiency with dissipation, such as lossy capacitors and resistors. I'll talk a little bit about how we do that, but we do that really efficiently with something called an adjoint method. So in circuit QED and in optics, you can always think about loss by adding a port. Like with this beam splitter model, you can make the electrical engineering analog of this, where if you have a resistor with resistance R, you add a port, which is effectively an infinite transmission line with a characteristic impedance equal to the resistance. But this really doesn't scale. If you're trying to compute something like a TUPA with 1,000 unit cells, then you'd have to add 1,000 ports to your system, and then you'd have to have 1,000 by 1,000 scattering parameter matrix. If you're simulating this at 10 different spectral modes, then it's going to be 10,000 by 10,000. It just utterly blows up. But using something called an adjoint method, you can, with 2 simulations, you can simulate there you're effectively time reversing the absorption of the resistor to find the input to each of your physical ports. And then with just double the simulation time, you can compute the effects of resistors. I would say you should iterate on your computer before you build, and this isn't a replacement for like doing the coupled mode equation analysis and solving equations, but it's a useful tool. And we absolutely welcome contributions from the community. So I just want to show a couple examples. For example, simulating a snail parametric amplifier, which is this cool Josephson circuit that gives you a purely three-way mixing interaction without creating a self-curve, so it doesn't shift the frequency of your amplifier depending on the pump bias point. We can simulate this in about 10 milliseconds for however many frequency points, 100 or something like that. You can use the exact Josephson junction potential. You can do as many modes. I think this was 16 pump harmonics and 17 signal and idler modes, and it takes like 20 milliseconds to simulate. So it's all open source. You can give it a shot if you're interested. And if we compare with WR-Spice, this time domain simulator, that takes like 2,000 seconds and gives the same results. Harmonic balance is often a much more efficient way to describe this. Can also simulate like crazy complicated devices like these impedance engineered JPAs or LISAs from the Google group. And one thing to note is that when you simulate these with commercial circuit simulators, they often require this auxiliary circuit to be able to get flux quantization. But we simulate things in the branch and node flux basis, so flux quantization just naturally falls out of this system. You can compare the gain curves and they look pretty similar. Okay, so this is simulating the devices with dissipation. So we can look at the gain as a function of frequency as we increase the loss tangent, the amount of dissipation in the dielectrics from no loss to a parameter called the loss tangent of 10 to the minus 3 to 2 times 10 to the minus 3 to 3 times 10 to the minus 3. And we see that as you increase the loss, the quantum efficiency starts to degrade. You go from perfect quantum efficiency to lower quantum efficiency. And we do this using these adjoint methods that I was describing. To simulate this directly by adding ports, it would be computationally intractable. And like I was saying, if you're interested, absolutely use this tool, contribute to it, improve it. I think our field has a great history of creating a lot of useful open source tools like SC qubits, KIC, etc. So and other tools. Okay, so now to get back to the devices, there's a vicious cycle of quantum efficiency and dissipation in these amplifiers. So this is plotting the quantum efficiency relative to the ideal as you increase the gain and increase the loss tangent. So you go from relatively high quantum efficiencies in a lossless system of say 90% to around 50% if you increase the loss tangent. And the idea here is that your pump is being absorbed, and so you have to pump it harder, which which makes this the sideband mechanism worse. And both of these together really reduce your quantum efficiency. So whereas in these Floquet tupas, then the quantum efficiency degrades relatively gently with loss. But we really want to be here in the upper right. And I'm going to tell you the fab techniques that we use to reach quantum efficiency in this quadrant. So to do this, we replace the capacitors in the device with coplanar waveguide capacitors. And we had this fabricated at MIT Lincoln Laboratory in their school foundry on a 200 millimeter wafer. Here you can see the beautiful wafer with the amplifiers as the highlighted in yellow. So they were literally co-fabricated with qubits in the exact same process. Here's an image of one of the traveling wave amplifiers where it's oscillating back and forth down the transmission line. This is one of the packages that my group developed that has is very modular and has high good microwave performance, low return loss, which I'm happy to talk more about in the tours. Okay, so how does this thing perform? Well, we can characterize the gain as a function of frequency with the pump on and the pump off. Pump on, we see over 20 dB gain. Pump off, we see less than half a dB of an in-band insertion loss. So this thing is really quite close to lossless. And then place this in parallel with something called the waveguide QED device, which is a qubit that we can use for power calibration. And we can see that this gives an intrinsic quantum efficiency of a full system quantum efficiency of 83.6 plus or minus 2.6%, and intrinsic quantum efficiency of 92.1 plus or minus 7.6%. So this is getting really close to an ideal parametric amplifier. And when we then put it in a qubit readout configuration, where we put the qubit in front of the tupa with an isolator and directional coupler in between, then we get a full chain readout quantum efficiency of 5.1%, which is basically on par with the best quantum efficiency that you can achieve with these narrowband JPAs. So I would say that now the typical knowledge that if you want the highest quantum efficiency, you should use a JPA is now sort of broken. And if you want and tupas can get you as high quantum efficiency. And we hope with the latest devices, we can actually get higher because we need less isolation between the qubits and the tupa. Okay, so now I want to shift gears a little bit. So these were MIT Lincoln Lab fabricated devices. Now I want to talk about building our own fabrication process on campus to fabricate these tupas and some of the challenges and things that we had to improve to be able to fabricate devices like this. And this was led by two students in my, or a postdoc in my group, Kaiyang Tang, and a student, Andres Lambo, as well as Eric Boyd. And this was done in collaboration with Will Oliver's Engineering Quantum Systems group, as well as our collaborators at MIT Lincoln Labs. So what we developed is a 200 millimeter wafer process for fabricating qubits and amplifiers. We made improvements to junction quality and uniformity, built an air bridge process, and fabricated qubits and amplifiers in this. So I'll tell you about some of the details. First, fabricating tupas is quite challenging. These are 5 by 40 millimeter chips. They have over 1,000 unit cells. They have over 2,000 bridge crossovers. They have over 1,000 phase matching resonators. They have over 1,000 Josephson junctions. And every single one of these Josephson junctions needs to at least not be an open. If one single Josephson junction is an open, your entire device is toast. And when you actually go and fabricate these things, you'll have debris, scratches, junction opens, junction shorts. So you have to basically get everything right for this to work. So it's hard. And I think it's also interesting because we're facing a lot of these scaling and yield challenges sort of before people making quantum processors are seeing these. So for this slide, I'm going to define yield as not open, but later we'll define yield as plus or minus 20%. Because one junction open will prevent waves from going through this transmission. So if we look at the probability of a single device working as a function of the rate of junction opens in parts per million, we see that by 1,000 parts per million, you only have a 20% chance of your device working. But we want not just to make one wafer and have one device work, we want all the devices to work, or almost all the devices to work. So if you look at the wafer scale yield of, say, 100% of the devices working, then you see that you need a rate of junction opens on the order of 1 part per million. And as you increase the number of junction failures, you see that the yield dramatically drops. The probability of getting 90% of your devices working, it'll drop around 100 parts per million. So you really need a high reliability junction process. And not only do you need the junctions not to be open, but you also need the junctions to be very uniform. And the way to think about that is, if you look through a piece of glass, like a clear piece of glass where it's uniform, then you can see, you might get a reflection at the edge because of impedance mismatch, but you can see through it. But if you have a glass where the properties vary as a function of position, it'll look frosty. And that's sort of what happens with these tupas, where you'll have reflections inside of the devices, and that will increase the ripple in. So if you plot the ripple in the gain variation as a function of frequency, you see that to get a ripple of less than 0.2, which would be less than 3 dB, you need a junction relative standard deviation less than 3%, which is pretty challenging to achieve. So in developing this process, you can plot all the processes in literature, and we care not only about the relative standard deviation, but the relative standard deviation over a large area. So if we look at the relative standard deviation of different processes, we can see that we're able to hit very low relative standard deviations comparable to best over a large window. And I'll tell you some of the tricks for doing this. So one was using a Dolan process and optimizing the heck out of the MMA, the lower resist thickness. So the Dolan process is, you have a freestanding bridge and you evaporate your aluminum from one direction, you oxidize it, and then you evaporate the aluminum from another, and this overlap region forms the Josephson junction. And this overlap area, it depends on the angles, it depends on all the geometric dimensions, and it also depends sensitively on this resist thickness. And we found that if we make this bridge width large and increase and really optimize the MMA thickness, we're able to get high. So for example, this is a ellipsometry of a 200 millimeter wafer, showing that the resist thickness is only varying from 694 to 704 nanometers. And this is less than 1.6% resist thickness variation. Okay, we also implement large scale electrical testing for both qubit, amplifier, and junction chains. Qubit junctions, which are like tens, hundreds of nanoamps, amplifier junctions, which are microamp, and chains of junctions. So we routinely electrically test like tens of thousands, around 100,000 typically, Josephson junctions on a test wafer. And we measure a relative standard deviation for the large 800 nanometer overlap Josephson junctions as a function of junction length in the process window for making these tupas of less than 2%. And we can compare this to the 200 nanometer junctions, which have a higher RSD. So by making your junctions bigger, you decrease the variance, which kind of makes sense. But you also have to optimize the resist thickness. And one cool thing we implemented is we can electrically test these whole wafers. And then we do this with code, obviously. And then in that code, we can flag any junction that fails the electrical testing or is somehow anomalous. And then we program a scanning electron microscope to go in and automatically visit all the locations on the wafer that have failed junctions. And then we can analyze them and see why they failed, what we need to change in the process. And I guess right now that's done sort of manually by student postdoc us. Maybe it would be cool to train an AI or machine learning algorithm to do that. But that's future stuff. Okay, we also implemented a dielectric crossover process. We did this because often people use air bridges in the community where it's a freestanding bridge. We didn't want to fight problems of junction yield as well as bridge yield at the same time. So we just did this silicon oxide crossover process from the Google group, and we find that this gives 100% yield for wafer scale uniformity for testing like 15,000 bridges. But it does induce a little bit of loss because of the silicon oxide. So how well does this work? Well, we can look at a TUPA fabricated in an earlier version of the process that has about 5% relative standard deviation. We see that it has some ripples, whereas the TUPAs fabricated in the latest version of the process that are well impedance matched, they have relatively small ripples. And these TUPAs have high gain, over the 25 dB gain over a broad range. And this ripple can be improved with impedance matching. We have some devices that are better matched. And not only do they have high gain over broad bandwidth, but they also have high signal to noise improvement over a broad bandwidth. We see over 11 dB SNR improvement over 4 gigahertz of spectrum. And we're working on doing the power calibration for these devices, but this is the same setup used for calibrating the Floquet TUPAs that we measured previously, and their 10.23 dB SNRI resulted in 83% full chain quantum efficiency. So we're quite optimistic about these new devices. And so should I end at 12:45 to give time for questions, or ish? Yeah. Okay. So I want to talk about some of the things that I think we should be doing with TUPAs that TUPAs will enable for qubit readout. So one is that most people, when they're operating TUPAs, they just leave them on. Whereas I think it makes a lot of sense to pulse them on and off. And this is because, and I recently learned that from the Google team is actually doing this with their Josephson junction parametric amplifiers. They pulse their JPAs on and off, and that allows them, or I guess the general motivation is that this allows you to remove isolation in between your qubit and your amplifier, because there's less chance for your pump and other things to dephase the qubit during when you're not reading out the system. So TUPAs, because they have such a broad bandwidth, they actually have less than a 20 nanosecond device. And this is insignificant compared to most readout times. So you can just turn your TUPA on when you're. Another thing that we're working on is developing reflectionless filters. So you can go and buy these at mini circuits. I'm sorry to say that they use tantalum nitride as the resistor material. So if you go and cool these down, you'll find that unfortunately they're no longer reflectionless because their resistor has turned into a pretty decent superconductor. But the work of Ben Palmer's group at LBS showed that you can build a nichrome process, and that these resistances are relatively stable at cryogenic temperatures. So we replicated that process and used this to design these reflectionless filters. And the motivation here is that often we need filtering in superconducting qubits, but typically the filters that we use, they reflect everything that they don't pass. And this, particularly for amplifiers, is quite bad, because then you create cavities, you create standing waves, you create parametric instabilities. And I think this also causes problems for other parts of qubit readout or qubit readout control, just things, pulses bouncing around inside of your system. Whereas these reflectionless filters, you can design a pass band, and everything in and out of the pass band will just be absorbed internally in resistance. And I think another interesting direction that we're working on is non-reciprocal traveling wave parametric amplifiers, where in the reverse direction they absorb everything when the amplifier, whether the amplifier is on or off. And one of my students presented this at March meeting, where it's a 4-port device. There's an adiabatic 180-degree hybrid at the input and output of the device. You have a set of coupled nonlinear transmission lines inside of the device, where you pump both of the lines, and the pumps mediate a process that converts from the signal on one band to the idler on the other band. And then, so you sort of hop from one mode to the other, and then that mode escapes over here. Whereas in the backward direction, you don't have phase matching, so you don't get this conversion process, so you can block everything passively. Everything is just routed into this port. So we think that this is a path for making TUPAs that also isolate. Okay, so maybe I'll conclude just to leave time for questions. And if people are interested in the ultra-strong coupling work, happy to show a couple slides on that, just ask. So we've shown that sidebands and insertion loss reduce the quantum efficiency of TUPAs. Told you a little bit about this JosephsonCircuits.jl package for all of your superconducting qubit, SPICE, and parametric device simulation needs, and told you about our experimental demonstration of these high qubit devices. So with that, I'd like to thank all of you for listening, thank my group, and thank the sponsors of our work.
So if I understood like how these Floquet tubers work properly, it's that you kind of adiabatically turn on the tuber and then like adiabatically turn it off, and it's like converts the input into like the mode you want, and then like it converts it back to the output. Have you looked into these?
Sorry, one.
Yeah.
We do that in the spatial domain.
Yes.
I think that's important.
Yeah.
Go ahead.
Okay. Have you looked into these like shortcuts to adiabaticity works, where like you can like design that shape just right so that like you can do this much faster?
Yeah, I mean, I've definitely thought about doing that, but we have not done that yet. I think that there are probably more optimal ways of doing that. We sort of design this profile heuristically, and actually in the experimental paper, we don't actually use this profile. We make it more of a flat top in the center and with a ramp up and a ramp down. And that's because you want, once you get into the right Floquet mode, you can just have this longer straight section that where you get more gain and then ramp down. I'm certain we're not doing it in a mathematically optimal way. So that would be a very interesting thing to look at. One thing to take care of is that we do want performance over a broadband. So I think whatever shortcut to adiabaticity schemes you do, we'd want to make sure it doesn't compromise the band. I sort of think about like this as sort of like impedance matching in electrical circuits, or mode matching, where there are broadband impedance matching strategies, like you can impedance match two transmission lines by adiabatically varying the lengths for the characteristic impedance. You can do like more clever things like Kloffenstein and stuff, tapers that have can do this over a shorter spatial range, but they might have some bandwidth constraints. You can also do things like quarter wave transformers that really short, really narrow band. So I would bet that there are like clever strategies that one could do. Great question.
Since these new Floquet tubas are potentially compatible with the Lincoln boundary process, are there any plans for them to switch over to making these tubas? Since if they can address the like yield or challenges, it seems like they're just uniformly better than typical tubas. Are there any discussions about that?
Yeah, there actually are. So we're funded. Our team is funded through the IARPA Entangled Logical Qubits program to provide these Floquet tubas to the community. And for people even not part of that program, just like send me an email and we'll see if we can make it happen.
And then another question for like the yield of your junctions across the wafer, that's super incredible. And your like MMA thickness, do you account like that in the size of the junction form? Like, do you say that in some of those low regions you actually want to make the GDS structure larger or smaller as a result of that? And then also, do you consider the like angle divergence of your lumen source in this as well?
Yeah.
How precise do you have to get this incredible like mode?
Yeah, I mean, these are all great questions. So so the angle, for the MMA thickness variation that we have here, the variation due to the angled deposition, for people not in superconducting qubit community, you evaporate this with an electron beam evaporator, which like shoots electrons at a pool of metal, and then atoms fly off, and it flies off in a plume. And you deposit your JJs by angling your wafer, doing those angled depositions. And because parts of your wafer will be closer to this plume, and because this plume has some angular divergence, you'll see some variation in critical current across the wafer. So we don't compensate for that now. And I might mention that the Dolan process from a paper from the Nakamura group actually partially compensates for this because you do one evaporation at this angle and another evaporation at this angle, it helps. We would like to do that, but really it's been the proximity effect correction computation time that's prohibitive to us because we would need to do PEC for each of the different sizes. And this is done on a shared, something we have to pay by the hour for and compete with a bunch of other people. So it's just challenging to do, but maybe getting our own dedicated computer that could run these PEC calculations for 24 hours or something would be a way to do it. And did you have another question or?
I think those were maybe another follow-up is, are you potentially willing to share some of those like junction code structure GDS files? I think that could be useful for the community of other people who are trying to make reliable junctions.
Yeah, I think so. Yeah, great.
Hi there, this is maybe a naive question, but those gain ripples, are those in some sense real? Like if I'm looking for a narrowband signal, do I get some advantage by parking on one of those ripples upwards versus being in a ripple downwards, or are those?
Yeah, so I think one thing to note is that when you're doing qubit readout, it's really the gain of the first amplifier. When you're doing it, it's really the gain of the first amplifier that matters the most. And the criteria is that it's enough gain to like kind of overwhelm the noise of the second amplifier. So often you design your readout chain such that like maybe 20 dB gain overwhelms the gain of the next amplifier. So you don't really get a big SNR improvement for like parking on these gain ripples. For example, I guess here we see we're plotting this as a function of pump power, and the gain is increasing from like, I don't know what the value, maybe 10 dB here to 15 or 20 or 30 dB up here. And if you look at the same plot for the SNR improvement, you find that the SNR improvement sort of saturates over a broad region. Maybe there's some increase with increased gain, but it's not really a big improvement. So I typically wouldn't try to park at like the gain. And often we want to achieve like low ripple so you don't have different amounts of gain for different readout resonators, just to make two.
Right, but I guess going back to that SNRI plot, like there are still vertical stripes. Like there are certain frequencies that have better SNRI than others. If that's like a real feature of this particular device.
Yes.
If I had a signal that was at one of those peaks in SNRI, I would be better at looking for it than a signal that was in front.
That's right. That's right.
Okay.
Yeah, but I mean it's not like huge necessarily. That's
right.
like
Right. It, yeah.
10 to 12. Yeah.
I'm coming from this from the like axion search angle. So looking for narrowband, very weak signals is what I'm thinking about. Cool. Yes, thank you.
Yeah, no, I'm definitely, like I said, I love for these to be, I'm happy they're useful for qubit readout, but other things like axion searches, dark matter searches, I think these are all really, really interesting applications. Happy to chat.
Yeah, so I mean, I think what's really nice about this is that like you kind of built this general framework to be able to treat these things, and the amplification is usually done in kind of like a weak nonlinearity regime, which is good for down range and stuff. I'm kind of curious about in more of a limit where you have a strong nonlinearity. Have you consider that? Like, you know, I've always like dreamed that one could make, you know, traveling with a quantum computer sort of things in it, you know, what photonics would dream of, but it should be possible with Josephson.
Yeah, so I guess I'll answer it from a couple different directions. So from the simulation perspective, the harmonic balance solver it's a multi-tone harmonic balance solver, so you can put in multiple strong tones and simulate what's going to happen. So when you think about, so typically when you're doing like gain simulations, you'll simulate it with one strong pump, and then that gives you like then you simulate, you think of it as a 1D grid of harmonics. If you send in 2 strong signals, then it's like a 2D grid, and you have to simulate everything on this 2D grid. It's 3 strong signals, 3D grid, so your computational space, like it really grows as to the nth power the number of tones. So we can simulate those things. And I think for readout applications, these interactions between stronger tones, it typically generates something called intermodulation distortion, which can degrade the quantum efficiency of your devices. But I think what you're talking about is more kind of designing these intentionally to be more nonlinear, and then like using the interactions between tones to perform some computations. I think that would be totally possible, and could actually be interesting now that these devices have low loss. Yeah.
Another question. I feel like there is like analog to this in like fiber amplifiers. How much have you like taken from field and applied it to tubas? And is there anything in the reverse direction that you can improve how fiber amplifiers work based on what you learned here?
Yeah, no, great question. So I like Dave was mentioning, I come from optics and I'm like super familiar with all the fiber amplifier stuff. I would say there are we use some different techniques. Like there are a bunch of uniquely nonlinear fiber phase matching techniques. We can develop some different because we can generate localized resonances. So for example, like we can generate IQ resonators all across the chip, whereas in fibers, that's not so easy. I think that just a lot of their frameworks, the coupled wave equations you use to treat nonlinear like effects in fibers, then really tubas, like the theoretical modeling tools. I think one way in which it could go the other way is we're in a situation where our nonlinearities are insanely strong compared to fibers. I forget the exact figure, but I think these tubas are like maybe 30 wavelengths long or 50 or something like that. It's like order of tens of wavelengths. Whereas your optical fibers are like, hesitate to say a number because it'll be wrong, but like billions and billions or something like that wavelengths long. But people in optics want to increase the level of nonlinearity, and that's going to create issues like these Floquet modes and stuff like that, that really only appear when you have these high nonlinearities. So I'm hoping at least some of these techniques could be applicable.
I was just gonna everybody thinking.
Oh. Great. Yeah, thank you so much.
So,